Welcome to our journey through the fascinating history of atomic theory. Imagine a vast universe filled with galaxies, stars and planets, all constructed from the tiniest building blocks imaginable, atoms. Let's explore how our understanding of the atom, this fundamental constituent of reality, has evolved over the centuries, from ancient Greek philosophers to the pioneers of modern physics. From philosophical ponderings to elegant experiments, our ancestors embarked on a quest to unravel the mysteries of matter. How could something so small, so invisible to the naked eye, hold the key to understanding the nature of our universe? This journey of discovery is a testament to human curiosity and our relentless pursuit of knowledge. Our journey begins in ancient Greece around 400 BC with a philosopher named Democritus. Democritus, along with his mentor Leucippus, dared to imagine a world where everything around us, from the rocks beneath our feet to the stars in the sky, was made up of tiny, indivisible particles they called atomos, meaning uncuttable. Imagine taking a piece of matter, say a golden coin, and dividing it in half, then in half again and again until you reach a point where it can be divided no further. This, Democritus believed, was the essence of the atomos, the fundamental indivisible building block of all matter. While lacking experimental evidence, this idea was a philosophical breakthrough, a seed planted in the fertile ground of human curiosity that would lay dormant for centuries, waiting for the right time to sprout and flourish. Fast forward nearly 2 millennia to the year 1803, a time when the scientific revolution was in full swing. An English chemist named John Dalton, drawing on the work of Antoine Lavoisier and other pioneers, resurrected the idea of the atom. But Dalton went further than Democritus, grounding his ideas in the emerging field of experimental chemistry. Dalton proposed a comprehensive atomic theory, stating that all matter is composed of atoms which are indivisible and indestructible. He envisioned these atoms as tiny, solid spheres like billiard balls, each element possessing its own unique type of atom. For example, all gold atoms were identical, distinct from the atoms of other elements. Dalton's theory went on to explain chemical reactions as the rearrangement of these atoms. When elements combine to form compounds, their atoms joined together in simple whole number ratios. His work provided a framework for understanding the behavior of matter at the atomic level, laying the foundation for modern chemistry. Our understanding of the atom took a dramatic turn at the end of the 19th century. In 1897, English physicist J.J. Thomson, experimenting with cathode rays, made a groundbreaking discovery, the electron. Thomson observed that these rays, emanating from a negatively charged electrode, could be deflected by both electric and magnetic fields. This suggested that the rays were not made of waves, as some believed, but rather streams of tiny, negatively charged particles. This discovery shattered the notion of the atom as a solid, indivisible sphere. Thomson proposed a new model, often called the plum pudding model, where negatively charged electrons, the plums, were embedded within a positively charged pudding that made up the bulk of the atom. The atom, it seemed, was far more complex than previously imagined. The early 20th century brought about another revolution in our atomic understanding, thanks to the groundbreaking work of Ernest Rutherford. In 1911, Rutherford, a New Zealand-born physicist, conducted his famed gold foil experiment, which would forever change our perception of the atom. Picture this: alpha particles, positively charged particles much smaller than atoms, were fired at a thin sheet of gold foil. Most of the particles passed straight through the foil, as expected if the atom was a diffuse cloud of positive and negative charges, as suggested by Thomson's model. However, to Rutherford's astonishment, a small fraction of the alpha particles were deflected at large angles, some even bouncing back towards the source. This unexpected result could only mean one thing. The atom was mostly empty space, with its positive charge concentrated in a tiny, dense nucleus at the center. While Rutherford's model explained the atom's structure, it still had limitations. Classical physics suggested that electrons orbiting the nucleus should continuously emit energy, eventually spiraling into the nucleus, causing the atom to collapse. This, of course, didn't happen in reality. Enter Niels Bohr, a Danish physicist, who in 1913 proposed a revolutionary model that addressed this discrepancy. Bohr's model incorporated the emerging field of quantum mechanics, which governed the behavior of particles at the atomic and subatomic levels. He proposed that electrons could only exist in specific energy levels, or shells, around the nucleus. These shells were quantized, meaning electrons could only occupy discrete energy levels, not just any energy level, as classical physics suggested. This model explained why atoms were stable and why they emitted light at specific wavelengths. When an electron jumped from a higher energy level to a lower one, it emitted a photon of light with energy equal to the difference between those levels. This explained the unique spectral lines observed when light from different elements was passed through a prism. While Bohr's model was a significant leap forward, it still relied on a somewhat classical view of electrons orbiting the nucleus in defined paths. In 1926, Austrian physicist Erwin Schrödinger revolutionized our understanding of the atom yet again by introducing the concept of wave mechanics. Schrödinger's model abandoned the idea of electrons following precise orbits and instead described them as existing in clouds of probability called orbitals. These orbitals, defined by mathematical equations, represented the regions around the nucleus where an electron was most likely to be found. This model, based on the wave-particle duality of matter, where particles could exhibit both wave-like and particle-like properties, provided a more accurate and complete description of the atom, consistent with the principles of quantum mechanics. It painted a picture of the atom as a fuzzy, probabilistic entity, a far cry from the solid spheres envisioned by Dalton just over a century earlier. By the early 1930s, our understanding of the atom had come a long way, but there was still one missing piece of the puzzle. While protons, positively charged particles in the nucleus, had been identified, the mass of atoms suggested the presence of another neutral particle. In 1932, James Chadwick, a British physicist, made a momentous discovery that completed our picture of the atom. Through a series of experiments, he identified the neutron, a particle with no charge, but with a mass similar to that of the proton. The neutron resided in the atom's nucleus alongside the protons, contributing to the atom's mass but not its charge. This discovery not only completed our understanding of atomic structure, but also opened up new avenues of research in nuclear physics, leading to the development of nuclear energy and the atomic age. Thank you for joining us on this enlightening journey through the history of atomic theory. From the philosophical musings of Democritus to the groundbreaking experiments of Chadwick, we've witnessed how our understanding of the atom has evolved over centuries of inquiry and innovation. Each discovery, each new model, built upon the work of those who came before, pushing the boundaries of human knowledge further and further. And as we delve deeper into the quantum realm, the atom continues to surprise us, revealing new secrets and challenging our fundamental understanding of the universe. Stay curious and keep exploring the wonders of science.